We are working with addition squares. In our efforts to help the students to add and subtract without counting, we have identified that a basic component is knowing the decompositions of all the one-digit numbers and the decompositions of 10. We work on this, let's say, abundantly. It's a lot of work for the students to familiarize themselves with the decompositions of numbers from 2 to 9 and then for 10. The thing is that after having done this, we need a way to record it. And addition squares are our strategy for recording the decompositions. It is in this manner that we have a decomposition of 7. We have a square that has 7 above it and below it. We look for 2 numbers that add up to 7, correct? And on the other hand, we very clearly relate the addition with the decompositions as almost opposite processes. It is also true that we understand that the addition square on its own is very abstract. The student must provide it with a context and has to do this independently. Right? When they see a square which has a 4 or 5 in the lower portion, then they must imagine a situation in which they combine 2 sets, one, for example, of 4 cubes and another of 5 cubes, and are asked how many cubes there are in total. This task of the student themselves putting forth an abstract question to indicate context is very important, because in this way, many abstract situations could be resolved, which otherwise could not be linked to their reality and with all the opportunities that they are given to resolve it. How to learn? Using this model provided by the teacher. That is, the teacher, when presenting the square, invites the students to imagine the situation that exists, very clearly understanding that it can be this or it can be another, but it is whatever you imagine that could help you to resolve it, correct? In an alternative example, we could have a jar that has 7 beads, okay? And we say, if in this jar there are 7 beads, then we cover it for a moment, and now there are 6. How many have we taken out? Or if we say to them, the jar after one operation has 7 beads, but originally it had 6, the child imagines the decomposition of 7 as 6 plus something. And so I ask you, what is the missing number? That is, when I have the addition squares, I can lack the number above, or I can lack the numbers, one of the 2 numbers below. Or it may even be that the 2 numbers below are missing. In this case, what I always do is draw upon a context, which will help me to solve the task. Draw as many additional squares as possible with 8 in the top box. As we said before, sometimes we want to fill in addition boxes when we have the top number, but not either of the 2 numbers below. Like in this case, we have number 8 at the top, and we have neither number below. We know there is a solution. We know there is more than one, but in these types of questions, we are focused on finding all of the solutions. We really want students to be able to apply a systematic way of thinking that ensures that they try everything and that they find all the squares, that they haven't repeated any, and that they're not missing any. This is clearly related to a much more competency-based approach, because we look at breaking down the number and problem-solving strategies. In these situations, the learner clearly has a problem that is not breaking it down, but making sure they find all the solutions. So, what we want is that they follow a certain pattern that helps them make sure that they're not missing any solutions. And that's why, when we have 8 at the top, they can start by saying, I can put 1 and 7 below, or I can put 2 and 6, or I can put 3 and 5, or I can put 4 and 4. At that point, there is a chance for discussion, one of those great opportunities that invites students to think. Are we sure we have them all? This is a very important point that depends on the model they are using to work out the addition square. If they are using a combination model, they don't need to move on to the missing solutions, 5 and 3, 6 and 2, and 7 and 1, because actually, combining 1 with 7 is the same as combining 7 with 1. But if you're modeling a situation using increasing change, it's not the same that there is 1 person on a bus and 7 get on, as 7 people on the bus and 1 gets on. It is clear that both situations lead to the answer that, in the end, there are 8 people, but the situations are completely different. So, in a situation of increasing change, it makes sense for students to duplicate the solutions. If they have put 1 and 7 in one, in the other they put 7 and 1. If in one they have put 2 and 6, in the other 6 and 2. With a combination model, it doesn't make sense. We can use the ones we already had, just 1 and 7, 2 and 6, 3 and 4, and no, that's wrong, 3 and 5, then 4 and 4. Okay? But even in this situation, there can be discussion. They might think that in that situation, 0 and 8 are missing, because a combination is that I, in this pocket, don't have any cubes, and in this one, I have 8 cubes. In total, I have 8 cubes, and a way of breaking it down is 0 plus 8, but often it depends more on the context than on the situation. What we do in these cases is say to students, let's see, what are you thinking about? And putting their specific situation into context, looking at whether or not they have done all the possibilities, that's really what's important. In combination cases, we have far fewer solutions than in cases of increasing change. And that is why, in some lab logbook tasks, we simply tell them to use situations as if they were thinking of a combination, so they don't duplicate solutions. How can the bridging through 10 strategy be adapted in the addition and subtraction of numbers between 0 and 100? With this lesson, let's say the strategies associated with addition and subtraction, we place the utmost importance on bridging through 10 as a basic strategy for learning to add and subtract without counting. This strategy of going through 10, or bridging through 10 as we call it, is very much based on breaking down numbers, as we just discussed, and decompositions of 10. Let's use 6 plus 8 as an example. If I have 6 objects, and I want to add 8 more to them, the first thing we have to see is that the 6 is calling out for the 4, because the 6 needs 4 to make it up to the 10. Therefore, the fact of having 6 as the first addend means that we need to break down the second addend, but we already know that one of the 2 parts, which we break down from the 8, has to be 4, because that's how I do it. Instead of jumping 8 from 6 all at once, what I do is break the jump into 2 pieces. So, from 6, I jump 4, and I get to 10, and as I have 4 more, I get to 14. That allows me to do 6 plus 8 equals 14 in a way that I don't need to use my fingers. I just need to jump from 6 to 10 in 4, and then jump by what I have left. That would be in the range 0 to 20, and it is essential to emphasize the range of 0 to 20 because, as we will see now, what we do in a higher range, 0 to 100, as we were just saying, in reality, it is exactly the same strategy. Let's consider, for example, 36 plus 28. That means I'm on 36 and I have to make 28 jumps forward. The first jumps by 10, 2 jumps of 10 or 1 of 20, however I like, I can do it quickly. I get to 36, 46, 56. Now I'm at 56, and I have 8 left to jump. But this situation at 56, where I'm 8 away, is exactly the same as when I'm at 6 and I'm 8 away. As it ends in 6, I need to break down the number that I have to 4 and what I have left. And so from 56, I make a jump to reach 60, and what I have left is 4, which takes me to 64. The strategy between jumps in the range 0 to 20 and any higher range from 0 to 100 is exactly the same. And for subtraction, it's also the same. The idea is, as before, we focus first on an example in the range 0 to 20, and then we see that what we can use in the range 0 to 20 is what we have to apply for a higher range. If we have a subtraction like 13 minus 6, we have a situation where we have 13 objects and we need to take away 6. But from the 13, I can also do it in 2 parts. First I take away 3, and then I'm left with 10. From 13, we have 10 and 3, so I subtract 3. That 3 means I can break down the 6 into 3 and 3. So I start at 13, I take 3, and then I have to take away 3 more. And breaking down 10 after taking away 3 leaves 7. So the relationship I am using between jumping along the number line and breaking down is just the same in addition as in subtraction. And I always need to break down 10 and break down the digit I am adding or subtracting. If I have a subtraction like 73 minus 46, in the basic calculation, nothing changes. I'm at 73 and I have to do 46 jumps backwards. Making 40 jumps backwards is counting down from 73 in 4 jumps of 10. So we have 63, 53, 43, and 33. Now I'm at 33, and it's necessary to jump down 6 more. And this situation is exactly the same as 13 minus 6. I'm at a number that ends in 3, and I have to jump 6, and I break down that jump of 6. I do a little jump of 3 that takes me to 30, and another jump of 3 that leaves me 3 below 30. From 30, if I go down 3, I get to 7, because we know that breaking down 10 with a 3 gives me 7, and that's how the subtraction equals 27. The difficult thing about these subtractions, which in another context we could say they are subtractions by carrying, is always in having to make the jump through 10, where I have to go through a 10 in one of the jumps, and I do this by breaking it down. And that's why it's essential to include the strategy of addition squares. What do we do if a student, to do 58 plus 19, begins at 58 and makes 2 jumps of 10 forwards and a jump backwards of 1? What do we do? Congratulate them, for sure. Congratulate them for finding a strategy that is efficient and ensure that their classmates understand this strategy and understand the benefits that this strategy has and can copy it. If it's a basic strategy to calculate quickly, When the jumps I have to make are 8 or 9, it's often easier to jump 10 and then go back. That's tied to something we already knew from when we put numbers on the necklace and we asked a child to put the number 9 on it. One of the things we encouraged was to not count from the beginning of the necklace, but to find the 10 and count backwards. This is the same strategy. If I want to add 19, the most efficient way is to add 20 and go back 1, because that's a very good mental calculation strategy. And by making jumps along the number line, we can understand why this strategy works. But it also means one student can tell another how they have done it in a class discussion. Some will make a jump of 10 and a jump of 10, then go back in a jump of 1. But another might make a jump of 20 in one go, and then jump backwards 1. And that's so much more efficient than making a jump of 10 and then 9 jumps of 1. And it's even more efficient than making a jump of 10 from 58 and then jumping 2 and then 7. We encourage bridging through 10, but that doesn't mean in any way that if a student finds a strategy that is even more efficient than jumping through 10, that we wouldn't applaud them and encourage others to use another alternative way of thinking. Do you think that calculation by counting is a must-have stage that should be transitional? We run the risk of it becoming extremely repetitive, but we really consider it a fundamental idea. You can't learn to add if it's not based on counting, because otherwise it would be totally decontextualized from what we actually do. It is imperative to learn through counting. But we have to do it in a way that, from the very beginning, the teacher knows it has to be a transitional stage. It is important that, if they have a crisis, the student knows they can always turn to counting to make sure their sum is correct. But from any point of view, we have to give them alternatives so that they stop counting. And when we see them counting, invite them to use other strategies, jumping through 10, making greater jumps, and then going backwards. But always encouraging the strategies they use to be efficient. We underline that the way we help students, from our perspective, is to focus heavily on going through 10, bridging through 10. And that is why we have insisted so much throughout this capsule on the use of addition squares as a way of recording the breakdowns that are basic to this strategy. What strategies can students working with the 100 grid and the number line follow to calculate 37 plus 19? We put a lot of emphasis on the number line as the basic model for communicating and thinking about strategies for jumping in addition. The idea is that we can't ignore using other models, and the 100 grid came up as a structured model for counting in the 0 to 100 range, so we believe it's appropriate to help students recognize that what they do using the number line can also be done on the grid. And some children may even see things more clearly and on a greater scale on the grid than on the number line, which helps them improve their strategies on the number line. The basic idea is that if I have a sum like 37 plus 19, and I want to do it on the grid, the basic idea is that I go to 37, and I have to move forward 19 squares. To go forward by 10, the first 10 squares means actually going straight down simply to the next line. So from 37, I go to 47, and from 47, I count 9 forward. Or, as we already mentioned, as 19 is a number so close to 20, I can start at 37, go down 2 rows, which puts me at 57, and then go 1 step backward, which gets me to the result of 56. The basic idea is that making jumps of 10 means moving on the grid vertically, and making jumps of 1 means moving on it horizontally.